Two problems with taping and stadiotachymetry are firstly, high accuracy is difficult and sometimes impossible to achieve, and secondly, they can take a long time if considerable distances are to be measured. Both of these problems can be overcome by using electromagnetic distance measurement instruments, and these are now used more than any other type of distance measuring equipment. The principle on which EDM is based is straightforward. If the distance between 2 points A and B is required, a combined EDM and theodolite unit is set up over one end of the line, and a reflector is set up over the other. The battery which powers the EDM system lasts for several hours. Replaceable or rechargeable batteries are available. The EDM part of the unit contains a transmitter and a receiver. The transmitter sends an electromagnetic wave towards the reflector, where it is returned and detected by the receiver. By comparing the incoming wave to the outgoing wave, the instrument calculates and displays the distance L. In order to understand how the instrument works, we need to know some of the properties of waves. In their simplest form, electromagnetic waves can be considered as periodic sinusoidal waves. The wave completes a cycle in moving from such identical points as A to E or D to H on the wave, and the number of times it does this in 1 second is known as the frequency of the wave, which has units of hertz. The wavelength of the wave is the distance it traverses in one cycle, and is usually given the symbol lambda. The period is the time taken by the wave to travel through one cycle, and is usually represented by t seconds. The speed, v, of the wave depends on the medium through which it is traveling. For example, the speed of an electromagnetic wave in a vacuum is known at the present time as 299,792,458 meters per second, and this is commonly called the speed of light, c. This can be approximated to 3 times 10 to the 8 meters per second. One other important property which is very relevant to EDM is the phase of the wave. This is the term used to identify fractions of a cycle or wavelength, and is usually represented by phi. The instrument measures the distance between the EDM unit and the reflector like this. When the transmitter is activated, it sends an electromagnetic wave towards the reflector, where part of it is reflected back to the receiver. If the transmission and reflection stages are opened out like this, then L is given by 2L equals n lambda plus delta lambda, where n lambda is the whole number of wavelengths travelled by the wave, and delta lambda is the incomplete wavelength left at the end. The instrument uses electronic devices to determine n lambda and measures delta lambda by using a phase detector to compare the phase of the outgoing wave with that of the incoming wave. The length L is then displayed on the instrument's readout. When designing an EDM unit, the manufacturer must decide what wavelength to use in the instrument. This will depend on the accuracy required. Modern phase detectors are capable of resolving to 1/10,000th of a wavelength, so if a measuring accuracy of 1 millimeter is required, the wavelength should be no longer than 10,000 times 1 millimeter, which gives 10 meters. And since the frequency of a wave is given by its speed divided by its wavelength, approximating the speed of light to 3 times 10 to the 8 meters per second gives a minimum required frequency of 3 times 10 to the 8 divided by 10, which equals 30 million hertz or 30 megahertz. Using a higher frequency will give a higher accuracy, but because of technical difficulties, the highest frequency on which phase comparison can be carried out accurately is in the region of 500 megahertz. Unfortunately, electromagnetic waves in the frequency range 30 to 500 megahertz are prone to being absorbed by the atmosphere, and so either a very large transmitter antenna or a considerable power supply would be required for a reasonable range. Neither of these are practical for portable surveying instruments. To overcome this problem, a process of modulation is used in which the measuring wave is mixed with a carrier wave of a much higher frequency. EDM systems use either amplitude modulation, AM, or frequency modulation, FM. In amplitude modulation, the lower frequency measuring wave is superimposed on a high frequency carrier wave to modulate its amplitude. In frequency modulation, the carrier wave has a constant amplitude, but its frequency varies in proportion to the amplitude of the measuring wave. EDM instruments are classified according to the type of carrier wave they use. The most popular EDM instruments are those which use infrared carrier waves, simply because they are the least expensive. They invariably use amplitude modulation, and ranges up to 3 kilometers can be achieved if sufficient signal can be reflected back. The type of reflectors used with infrared instruments take the form of corner cube prisms known as retroreflectors. They are constructed from the corners of a cube of glass which have been cut away in a plane, making an angle of 45 degrees with the faces of the cube as shown. The inner surfaces of the cube are highly silvered, and any wave hitting one of these will be turned through 2 right angles and reflected back along a path exactly parallel to that along which it was transmitted. This will still be the case even if the prism is misaligned by as much as plus or minus 10 degrees, so precise alignment is not necessary. Just point the prism towards the instrument using the sights on its top. It can be mounted on a detailed pole like this, or it can be mounted on a tripod. Here's another example. For longer ranges, more than one prism is required to ensure that enough signal is returned, and it is usual to increase the number by a factor of 3. For example, to a 3-prism set, or a 9-prism set, and more prisms can be used if required. EDM infrared instruments are invariably used in conjunction with theodolites, and they can be combined in one of 2 ways. Either the EDM instrument comes in the form of a separate add-on unit, which fits onto a special bracket mounted either on the theodolite or on the telescope as shown here, or the EDM instrument and the theodolite are permanently combined into one complete system. Both types of configuration provide complete angle and distance measuring systems in one unit, and for that reason are sometimes called total stations or electronic tachyometers. All infrared EDM systems automatically display the distance, and most also provide the facility to continue to measure the distance and update the display every few seconds.